Hello, this is Mr. Rasmussen with Algebra 1 and Lesson 117. In this lesson, we build off of Lesson 113, where we introduced direct relation or variation and inverse variation. So today, just a little adjustment, you can see the squared part in there. So using example 1 with distance and velocity, let's just review let's review what our direct variation and variation is first of all. So direct variation is where if one goes up, the other one goes up. And we can do that two ways. First of all, we can do that as direct relation. We can use our constant in there and as a scale factor and do it in two steps. Remember that. Or we can set it up as d1 over d2 is equal to v1 over v2. Okay, through a ratio. Then that's the direct variation. The inverse variation, remember, flipped it. So if we use our two-step problem and solve for our conversion factor in there, it would put it like that, where we put the v on the bottom. And that's where if d goes up, v is going to go down and vice versa. In the ratios, we do d1 over d2 equal, and then we flip the second part, v2 over v1, and I believe that worked I believe that worked there for finding it through the ratios. Now today, with the squared, you can see in the beginning of the lesson there, they use the W and the D for weight and distance. Basically, it says it's inversely squared with the distance, or the square of the distance. So in that case, all we do is put a squared into our problem. So if we were to do that for velocity, square velocity, we'd square the velocity, square the velocity, square the velocity, square the velocity on each one of those, put squareds in there. And you can see in the fourth example there, the strength of a field is inversely proportional to the cube of radius. Well, you see they just put a cube inside of the ones that it applies. Okay, let's take a look at example 1. It says the distance required for an automobile to stop is directly proportional, okay, so not inversely but directly, to the square of its velocity. All right, so let's set this up. I'll do it both ways. So that's this problem right here, okay, the square of the velocity. It says if a car can stop in 200 meters at 20 kilometers per hour, if we increase the speed to 28 kilometers per hour, how long will it take it to stop? All right, so let's do it the first way. Our first distance is 200 meters, okay, and our velocity is 20, and then that's going to be squared. So 20 times 20 is equal to 400, and then we want to divide both sides by 400. So basically, our constant is equal to 0.5. Okay, so now we put that back in. So 0.5, and we don't know what our second distance is. That's what we're trying to solve for. But our second velocity is 28. And we'll square that as far as this. Okay, so 28 times 28 equals, we got 784 here, times our 0.5. So it cuts it in half. Our second distance, our answer is 392 meters. So when we go up 8 kilometers per hour faster, our distance required to stop actually almost doubles because it's a little more of a, because it's related through the square. Let's do it through the one step there with the ratios. So our first distance is 200, trying to find my second distance. It's directly proportional, so my first velocity 20 squared on top, and then my 28 squared on the bottom. Of course, this is 400. My 28 squared is 784, so it looks like that. So basically, we got to cross multiply. It looks like 200 times 748 divided by 400. It works out to is equal to my distance there. And if you do the math, it's going to give you the same answer, just a different way to do it. Okay, let's look at example 2. In example 2 here, it says the distance a body falls varies directly, once again, as the square of the time that it falls. If it falls 144 feet in 3 seconds, how far will it fall in 10 seconds? Okay, so what does that look like? Well, let's do the ratios this time. We got distance 1 over distance 2 is equal to, we'll do time 1 over time 2. And I did it that way because it's directly related. So what is my first distance? My first distance is 144 feet. Trying to solve for my second distance there. My first time is 3 seconds, and it's directly related to the square of the time. So I gotta put my square in there, and then I put 10 seconds in for my second time. So 3 times 3 is 9, 10 times 10 is 100. All right, we got to cross multiply here, so I got 144 times 100 divided by 9 is equal to my second distance. So put that into the calculator here and hit enter, and I get 1,600 feet. So even though it went only 144 feet in the first 3 seconds, those last 7 seconds, it's exponentially speeding up. And you can see how we did that there. All right, let's look at example 3. In example 3, it says the weight of a body on or above the surface of the earth varies inversely. Okay, so we're going to be flipping it, looking at that guy there. And with the square of the distance from the body to the center of the earth. So basically, the closer you get to the center of the earth, the lower that number is, the greater the number of the pull of gravity, and we kind of say that as weight. The larger the number from distance from the center, the less the pull, the less weight. So inversely proportioned and with a square in there. All right, let's do this one both ways. So we've got weight 1 is equal to my constant times my distance. And its distance is squared, and I wrote that wrong because that's a direct relation. So let's correct that. There we go, there's my inversely proportioned. Okay, and then my other one's going to look like this. Weight 1 over weight 2 is equal to distance 2 over distance 1, and then I got to square both of those. Okay, it looks like I'm trying to solve for if the body weighs, how much to weigh if it's that far. It looks like I'm always solving for this guy here and having to flip them. So I'm going to rearrange that here. I'm going to actually, let's rearrange. Let's put W2 over W1 is equal to D1 over D2. So if we just flip both of those, we get the same thing here. That's squared, that's squared. Then maybe we have less moving around there. Let's put in some numbers here. We'll do the one with the conversion factor first. So my first weight is 10,000 pounds, and that's equal to my constant over top of my distance, which is 5,000 squared. Okay, so that is the same as this one coming up here. Let's change some things to scientific notation. We got 1 times 10 to the 4th there. This one here is going to be 5 times 5, right? 25, and then 6 zeros. So 25 times 10 to the 6th, right? And if we combine those, it looks like we get 25 times 10 to the 10th. Okay, for our constant. Okay, let's put that in and then solve and find our new weight there. So put our constant at the top. 25 times 10 to the 10th, okay, is equal to our weight number 2. Our distance number 2 is going to be 50,000 squared. Remember that squared is in there. All right, so 50,000 squared looks like 25, and I got 4 zeros, so it's going to be 8 zeros, so times 10 to the 8th. And let's put the, well, 25 divided by 25 cancel each other out, so that's 1 and that's 1. Let's bring this up, right? So it becomes times 10 to the negative 8, so exponents 10 minus 8. We can answer 1 times 10 to the second, which is the same as 100, and 100 pounds is our answer for example 3. Okay, let's work on the one practice problem there. Oh, I was going to do the other one the other way. Let's do that as well. Okay, for example 3 there, if we did the ratios, we've got weight 2 over weight 1. I flipped that so I didn't have to keep moving things around as much. All right, we got distance. The distances are squared. This one is the first distance, this is the second distance. So if we were to put this into that other problem there, it looks like my first weight is 10,000. There we go. I'm trying to solve for my second weight, and that's equal to, over here, my first distance is this, like that, and then my second distance is the 50,000, right, like that. So once again, this one here, 25 times 10 to the 6th, 25 times 10 to the 8th, and this is 1 times 10 to the 4th. So this one would come up, 25s would cancel out, this would make, those two would make that a 10, that 8 would come up, same problem. Okay, just set up a little differently. I tend to like the ratios a little better, and but I'll do the practice problem both ways once again. I'll do the ratios first though. All right, practice problem says the weight of a body on or above the surface of the earth varies inversely with the square of the distance from the body to the center of the earth. So basically same as our example problem there, number 3. All right, so if it's the same, we'll use this same setup there. Varies in distance with, so if my body weighs 50,000 pounds, so first weight is 50,000. I'm trying to find the second weight at a distance of 600 miles, so 6,000 miles. There's my first distance on top, inversely proportioned. How much would it weigh if we go 25,000 miles? Okay, so notice if my distance is going up, my weight is going to go down. I'm going to get a smaller answer than 50,000. Okay, let's change some things to scientific notation here. We got 5 times 10 to the 4th. This one here, 6 times 6 is 36. And then double my zeros, so times 10 to the 6 zeros. This one here is going to be 25 times 25. That is 625 times 10 and then 6 zeros there. Okay, so cross multiplication brings this up to the top. Let's rewrite this here as 336 times 10 to the 6 times 5 times 10 to the 4th over top of 625 times 10 to the 6th. Okay, let's multiply some things out here. 36 times 5, that gives me 180 times 10 to the 10th. So, all right, looks like I'll do, I'll bring my other one up, so times 10 to the negative 6, that gives me times 10 to the 4th, and then we'll do 180 divided by 624, which is a decimal of 0.288. So, let's remove our scientific notation part, which means I'm going to move the decimal place 4 places. So 1, 2, 3, 4. And it looks like my answer is 2,880 pounds is what my new weight is going to be. Okay, if we were to do that through the two-step problem, let's back up and do that to find a conversion factor. My first, I'll use, let's see here, I'll use this here. My first weight is 5 times 10 to the 4th, which is same as 50,000 there. And that's equal to my conversion factor divided by my first distance. My first distance is 6,000 squared, so I'll write that in as 36 times 10 to the 6. All right, and then so I'd multiply those two. 5 times 36, that's my 1/80. That's this right here. So my conversion factor ends up being, you can see how you're doing the exact same math. You're just doing it in 2 steps. So this is my conversion factor there. And so when I put that back in, my weight number 2 is going to be equal to 180 times 10 to the 10th divided by my second distance. My second distance looks like it is the 25,000 squared, which is the same as 625 times 10 to the 6. So you can see we're doing really the same math. Divide that out and you get 0.288. Bring this up times 10 to the 4th, and then we move that and same thing there. Okay, feel free to contact me if you have any questions, and have a great day.